San Diego. Alex Lee is a PhD student at UC San Diego, working with Professor Mark Myers. He got his undergrad from UC Berkeley and his master's from Columbia University. And he has spent time at Lawrence Livermore National Lab, working in the computational chemistry and materials science internship program. And today he's going to talk about simulating shock in silicon and diamond carbon. Please take it away, Alex.
Yeah, thank you, Farhat, for the introduction. So welcome to my talk today on the research I've been conducting for my PhD here at UC San Diego. It's been focused on simulation of shock compression in covalently bonded materials and primarily focused on silicon and diamond carbon. So I'm a fourth-year student in the Myers Research Group, and this work has been done with support from CMEC, the Center for Matter Under Extreme Conditions, and in collaboration with Dr. Rob Rudd and the Computational Chemistry and Materials Science program at Lawrence Livermore National Labs. So what is the importance of this research? Well, silicon and diamond carbon are both very interesting materials for the modern day. Silicon is an important material for many aspects in the industry, and is also a model material for simulations and experiments due to the ease with which perfect single crystalline samples can be created. Diamond carbon has always been an attractive material for a variety of reasons, such as its extremely high hardness and its low compressibility. More recently, diamond had a huge part in the National Ignition Facility's mission to achieve fusion ignition, which resulted in their net energy output from the fusion reaction. In their experiments, diamond carbon was one of the key materials as it was used for the fuel capsule, which holds and compresses the deuterium and tritium inside. Diamond also has its place in planetary research. The pressures and temperatures present on Neptune and Uranus make it possible for carbon to vaporize and rise through the layers of the atmosphere, then condense into diamond chains and rain back down in a type of carbon cycle. Exoplanet research has also found several carbon-rich planet candidates, such as 55 Cancri E, where there is more carbon than oxygen present on the planet, drastically altering its development compared to silicate or water-rich planets like our own Earth. Both of these materials share the same basic diamond cubic crystalline structure as well. Because silicon is better studied, we hope that some of the findings for silicon may have their counterparts in our efforts to understand more about carbon diamond as well. So the direction of my research is to understand the behavior of these materials when under shock compression. Shock compression is a dynamic mechanical process defined as a large amplitude wave across which there is a discontinuity in the pressure, density, particle velocity, temperature, and other properties before and after the wave. Common setups for producing shock waves include gas guns, where a flyer disk is accelerated to several kilometers per second, or laser ablation, where laser energy is delivered to an ablator, causing it to heat up to millions of degrees and hundreds of millions of atmospheres of pressure. This laser heated material is then propelled away at a high velocity, causing the remaining material to accelerate inwards. This method is the same as how some rocket propulsion works. In solids, this one-dimensional loading and inertial confinement results in a state of uniaxial strain. Shock waves travel faster than the sound speed of the material, with a shock velocity that is dependent on the amplitude of the wave. Shock wave behavior in a material can be compared to how a snowplow operates. The snowplow is moving at a velocity of UP, pushing the snow and the snowpack directly in front of it at that same velocity. However, snow is continuously piling up ahead of the snowplow, and this region separating the fresh snow from the packed snow is moving at a velocity u sub s. Empirically, a linear relationship called the shock wave equation of state is observed for most materials between the piston or particle velocity and the resulting shock velocity. The Rankine-Hugoniot equations are derived by applying the conservation of mass, momentum, and energy across this discontinuity, and describes the state of matter before and after the discontinuity of the shock front. Shock waves in experiments can reach extremely high strain rates of up to 10 to the 8th or 10 to the 9th. The large strain rates may suppress other more conventional deformation modes, such as fracture. This can lead to shock compression experiments having unexpected results, such as dislocations or phase changes that are not predicted from static compression or equilibrium conditions. These high strain rates also lend themselves to be very complementary to molecular dynamics simulations. Molecular dynamics is a simulation method to analyze the physical behavior of atomistic systems. At its core, individual atoms are modeled using Newton's equations of motion to see how the system evolves. The forces on each atom in the simulation are calculated to determine their trajectory. All the atoms are advanced in time. The forces are recalculated, so on and so forth. The way these forces are calculated are through something called interatomic potentials. These potentials describe the force between an atom and its neighbors based on a range of factors such as distance, bond order, embedding energy, quantum mechanical calculation, etc. These potentials can be derived in many different ways with a range of complexity, from the simplest Leonard-Jones potential to the recent advancement in machine learning potentials. The accuracy of the potential translates to the accuracy of the resulting simulation. Here's a list of just silicon interatomic potentials that have been developed in the past few decades. Each potential has its own physical basis, but each potential can be fitted to a variety of factors for its intended use. The same potential could be fitted to solid or liquid data, for higher or lower pressures, or for different phases of the material. Our potential of choice for our silicon simulations is a modified version of the Tursoff potential. The original Tursoff potential was initially developed for silicon and is a modified two-body bond order potential that incorporates structural chemistry into its framework. The A term here describes repulsive forces, while the B term here describes bonding forces, including the bond order and local environment. Any considerations for bond angles, competing bonds, and bond strengths are folded into this B variable. F sub c is the cutoff function, which limits the range at which atoms will interact with each other. This substantially lowers the computational load of the simulation. Tursoff's initial parameterization values for the potentials are seen on the right, and these more faithfully model the elastic properties of silicon compared to the potentials that came before it. The modified version of the Tursoff potential that we use in our silicon shock simulations was developed by Kumagai et al. And compared against several other silicon simulations in previous work by Shiteng Zhao and Eric Hahn. The modified Tursoff potential predicts the onset of plasticity at 0.82 kilometers per second. This compares well with experimental data, whereas other potentials such as the Ehrhart-Alby or Stillinger-Weber potential require piston velocities of up to 2 kilometers per second to induce plasticity. Other factors for use of its validation include development of dislocations along predicted slip systems and the use of density functional theory to compare stacking fault energies. This potential also predicts amorphization, which is validated by Zhao's shock experiments, where amorphous zones were observed upon recovery and characterization of the silicon samples. For my research, the tools used were LAMPS, the large-scale atomic molecular massively parallel simulator, and an MD simulation program that was developed at Sandia National Labs. OVIDO is used for the visualization of the atoms, and the supercomputing clusters at Lawrence Livermore were used to power them. The goal of my silicon research was to recreate and expand upon Zhao and Han's work previously on silicon. Our silicon simulation is set up in much the same way as theirs was. The bulk silicon is oriented in the 001 direction. A portion of the single crystalline silicon is cut off to use as a piston, as seen here. This block is frozen such that none of the atoms in it experience any force, but it is still able to interact with the rest of the silicon sample as it is accelerated into the bulk. This simulation was 25 nanometers by 25 nanometers by 300 nanometers, containing around 10 million atoms. The initial temperature for the silicon bulk was set to 300 Kelvin. We varied our piston velocity for these simulations between 0.9 and 1.5 kilometers per second, and the video seen here is going at 1.25 kilometers per second. At this piston velocity, the corresponding shock pressure should reach around 13 gigapascals, which is above the threshold expected for amorphization in silicon. In the simulation, the blue atoms are recognized as diamond cubic. Light blue or green mean that they are first or second nearest neighbor diamond cubic, and the white color means that they are in an unidentified phase. We see an angled bands of these unidentified phase propagating throughout the silicon bulk after the initial elastic wave has passed through. On the left here, we can see a close-up of the non-diamond atoms within the system. One of those bands was cut out and imaged face-on, as seen here on the right side. When these cutout bands were tested for strength and for energy, we found that there was very little strength in these bands, and that the difference in energy per atom between the diamond phase and this phase was about 0.3 electron volts per atom. On the right-hand image, you can see that there is also a lot of long-range order that is still present within the system, although there are small pockets that may contain an amorphous phase. The goal of my research here was to easily identify the phase of these unidentified bands. We decided to try matching our shocked sample to known structures for silicon. Beta tin, seen here, is the expected equilibrium phase for these pressures, but there are metastable phases that exist, especially under the short timescales and kinetically inhibited conditions of shock compression. Some of the other phases that we tested against included the BC8 phase, the ST12 phase, the BCT5 phase, simple hexagonal, and simple cubic phases. Our first attempts at matching the structure involved the use of the radial distribution function. The example of beta tin versus our shock sample is shown on the left. We can see that the peaks are about in the same area, especially for the higher temperature versions of the beta tin structure. However, many of the other phases that we tested against showed similar results. On the right, we show the cumulative distribution function for silicon atoms of various phases. There are definitely some marked differences in some of these phases. For example, the simple cubic and the BC8 phases have a very sharp rise at about 2.3 angstroms, compared to the rest, which have a more gradual rise. However, there is still no conclusive match when comparing these against our shocked silicon sample. There is some extra information that we can find from this cumulative distribution function, as the value of the cumulative distribution function at a certain distance can be corresponded to the density of the atoms around a specific atom. We found that the most promising yet still relatively simple measurement for checking our structures against each other was using the angular distribution function. This calculates the angles between any three atoms in our simulation within a certain cutoff distance. Our shocked silicon sample can be seen as the green line here. We can see that none of these other curves quite match up perfectly, where they have different peaks or different valleys compared to the green sample. That is, of course, until we found our perfect match, which was BCT5. Here we can see that each of the peaks within our pristine BCT5 sample and our shocked silicon sample match up perfectly, although the shocked silicon sample is understandably more spread out. To confirm that this match was accurate, I went into the simulation to plot individual structures from both the affected regions of the shocked silicon and the pristine BCT5 structure. On the left here, we have the perfect crystalline structure of BCT5, and on the right here, we have the shocked silicon sample. The top views and the side views both match up nearly perfectly, although there is some wiggle room for the atoms in the shocked silicon sample due to thermal effects and the strain present within the simulation. Our next material of interest was diamond carbon. Diamond shares its base diamond cubic crystalline structure with silicon, but it is much stronger. It has a Young's modulus of 1050 gigapascals and a shear modulus of 440 gigapascals, almost 8 times that of silicon. In the Hugonio data for experimental shots on diamond, we see that piston velocities above 10 kilometers per second are used, with resulting pressures in the terapascal range. The shocks for diamond need to be much higher to reach pressures to observe any phase changes in diamond. Diamond's famous hardness and its bond strength mean that it is difficult to observe the presence of defects in diamond. However, previous work by Nia et al. Created diamond nanopillars with a focused ion beam and then performed in situ compression in transmission electron microscopy. They observed the presence of dislocation loops when the samples were compressed along the 011 and 111 orientations. These loops propagated along the 001 planes in their experiments, forming a trio of loops around the 111 axis. These static compression experiments showed that the anisotropic nature of defects in diamond have a very important relationship with the loading direction. To expand upon this, we wanted to probe how diamond would respond under different orientations when placed under dynamic shock compression under different orientations as well. During a ride-along shot we had with Camellia Stan at the Omega Laser Facility at the Laboratory for Laser Energetics, we had the opportunity to perform several experimental shots on diamond with recovery. But unfortunately, at the time, we only had samples prepared for shock along the 001 direction. Still, we can see here that the results of 200 joule 1 nanosecond shock reaching a peak shock pressure of around 80 gigapascals. After recovering the sample and analyzing it under TEM, we see that it retains its perfect diamond cubic structure with no dislocations or defects. The diffraction image here corroborates this perfect crystalline order in our diamond sample. For our simulations with diamond, we once again use the Tursov potential, this time for carbon. This potential has been shown to describe the mechanical properties of diamond carbon well for pressures of up to 150 gigapascals. Our diamond simulations are set up similarly to the silicon simulation, but with a wider X and Y and a shorter Z axis, with a total dimension of about 100 by 100 by 200 lattice parameters, or about 35 by 35 by 70 nanometers. This better captures the evolution of the shear components due to the wider range. This time our sample was oriented in 3 different directions along each of the 001, 011, and 111 directions to test the anisotropy of diamond under shock. Each orientation was subjected to a 3.5 kilometer per second piston velocity, which reaches around 130 gigapascal pressure for diamond. The 111 direction was additionally simulated at varying piston velocities from 2 to 3.5 kilometers per second. Each orientation was also subjected to the addition of a 4 nanometer radius void, which creates stress concentrations and encourages the development of defects within the simulation. For the 001 direction, our simulation results agree with what we see experimentally. As before, blue means diamond cubic, while light blue and green mean first or second nearest neighbor diamond cubic. Even at 3.5 kilometers per second, resulting in a peak pressure of 135 gigapascals, we see that no dislocations or defects are forming, just pure elastic compression. When a void is introduced, which acts as a stress concentrator, it appears that there is some activity above and below the void. However, this is simply the identification algorithm for the diamond cubic phase no longer working on the highly compressed areas. It is simply so elastically compressed that it could not be recognized. There are still no dislocations forming in this simulation, although there is some jetting and amorphization of material into the void. We also performed our simulations along the 011 direction. In the case without a void at 3.5 kilometers per second, we see even less activity compared to the 001 orientation. No defects form, simply elastic compression. However, when we introduce a void in the 011 case, we finally see some defects emerge. Here we can see symmetric defects emanating from the void at characteristic angles, which seem to be leaving behind stacking faults. Things get even more interesting when we tested shock compression along the 111 axis. Here we can see dislocations emanating from the planar impact surface, growing again at parallel and characteristic angles compared to each other. Many of these, because of the parallelicity of these bands, we think that they are acting upon similar slip systems. When a void is introduced, even more interesting things start happening. In this 2D slice of the simulation, we can see that there is an emanation from the void that is at a different angle compared to the rest of the dislocations going through this simulation. In addition, it is not leaving behind a stacking fault in its wake. It is likely that this dislocation is another type of dislocation that is acting along a different slip system that was not present in our simulation where it was just a planar impact surface. This three-dimensional view of only the non-diamond atoms in the 1-1 shock simulation shows what is happening. We have three sets of rectangular bands emanating from the void, seen here, here, and here, which are threefold symmetric about the void. And we have two sets of half loops connecting these sets of these three bands. We also still have some of these rectangular bands coming out from the planar impact surface at the same angle and direction as the band emanating from the bottom of the void here. Notably, there is a third half loop that is missing from this simulation. This side view of the non-diamond atoms can hopefully help to illustrate what is going on. First, the void is compressed and nascent dislocations begin to form at the most concentrated stress areas. The rectangular bands begin forming, leaving stacking faults in their wake. The half loops are near the end of the band, near the end of these rectangular bands connecting them. As the bands grow in length and move farther away from each other in three-dimensional space, the half loops also continue to grow to keep connecting them without leaving behind their own stacking faults. When we perform DXA analysis on the simulation, we obtain these values for the Burgers vector of those dislocations. The rectangular blue dislocations match up with those previously found in the diamond nanopillar compression experiments of Nia et al., forming along the 100 family of planes in the 110 directions. In the nanopillar compression experiments, these were instead loops, but our loops are instead along the 111 family of planes with a 211 direction. The most typical type of dislocation in the 211 direction for cubic systems is the Shockley partial defect, one of which can be seen here in the simulation. These typically have a Burgers vector of 1/6 211. However, our dislocations here are 1/2 211, which is equivalent to going from the bottom corner of a diamond cubic system to the top face center. Because of the large distance that this dislocation covers, we call it a super dislocation. This dislocation can also be understood as the sum of these two rectangular bands here, the 1/2 110 and the 1/2 101, which sum together to be the 1/2 211. It is believed that there might be some kind of reaction occurring between these two dislocations that causes this half loop to form between them. But still, we don't know exactly why this third half loop is not connecting these last two rectangular bands. In addition to the simulations for 111 diamond at 3.5 kilometers per second, we also performed simulations at varying piston velocity to see if we could find the threshold for defect generation. As low as 2.5 kilometers per second, or about 91 gigapascals of pressure, and without a void, bands of defects would successfully emanate from the impact surface. When the velocity was lowered to 2 kilometers per second and about 54 gigapascals of pressure, we no longer saw these bands form. But when a void was introduced, we did see the beginnings of dislocations starting to emanate from that void. We also tracked the propagation velocities of defects in the 111 case. These track the velocities of the stacking faults in the material with an additional measurement for the half loop dislocation in the 3.5 kilometer per second case. We can see that the piston velocity rises, so too does the propagation velocity, and we begin to approach the value for the shear wave velocity of diamond. In our DXA analysis of the 011 case, we can see that the stacking faults are instead occurring along the 211 direction in the 111 family of planes, with no sign of activity in the 100 family of planes. Additionally, only one slip plane seems to be active, symmetric across the void. To help explain the presence of these dislocations, we turn to a resolved shear stress analysis along the active slip planes of our diamond cubic system. Traditionally, for static compression, the Schmid factor is used to describe resolved shear stresses along slip systems for the case of uniaxial stress, and its form is given here. The relationship is defined by the cosine matrix, which relates the loading orientation against the slip direction vector. However, shock is not a state of uniaxial compression, it is instead a state of uniaxial strain. Transverse sigma 11 and sigma 22 stresses still exist in the lateral directions because of the single-dimensional strain condition. This complicates the calculation of the resolved shear stress in the system. To calculate the resolved shear stress for the case of uniaxial strain, we use a formulation called the Liu factor, which was developed by Chahui Liu for her doctoral dissertation previously here at UC San Diego. The stiffness tensor for diamond along the 001 direction must first be taken through a fourth rank tensor transformation into the new 011 or 111 orientations. We can obtain the strain in the simulation from the known piston velocity combined with a calculated shock velocity, with values for the shock equation of state taken from literature. The calculated stress obtained here must then also be transformed along the relevant slip system, similar to what has been done with the Schmidt factor, but involving more components since there are now more non-zero components to consider. We divide the calculated shear stress by the shock stress in the system to obtain the Liu factor. This results in the table that we see here. For loading along the 001 direction, we see that for the 001 planes, both the Schmidt and the Liu factors are 0, meaning that we expect no dislocation activity to occur, which is what we see in our simulations and in our experimental results. There does seem to be resolved shear stress in the 111 direction or 111 planes, but they are all negative, which means they're acting against the compression in the system and are much more unlikely to form. For the 011 case, we saw no activity in the 100 family of planes. These smaller values for the Liu factor could explain why we don't see anything there. However, for the 011 case, we do see activity along one slip plane. We can see that for the 211 plane in the 011 loading case, one of these slip planes has a much higher Liu factor compared to the other two, where one is negative and one is just smaller in magnitude. This could explain why we see only one slip system active in the 011 compression case. Finally, for the 111 loading direction, we saw activity in all three of the 100 planes. We can see that all three values of these are positive, although one is smaller than the other, but the 111 loading case had a smaller defect threshold for all the pressures, which could explain why we still see this one occurring compared to the lack of activity in the 011 case. And finally, for the 111 planes, we can see that two of these slip systems have positive values, and the final one is both small and negative. This could explain why we see only two half loops forming between these three rectangular bands and one that is missing. I also ran some additional diamond simulations at higher piston velocities and pressures to see if amorphization could be captured in diamond. However, the Tursoff potential is not well fit for these conditions, so results may not accurately reflect what actually happens to shock diamond. Nevertheless, there are some things that can be learned or compared with experimental data to see what could be improved in the future. At these speeds, the simulation time steps had to be slowed down as we start encountering errors in atomistic collision, resulting in longer simulation times. Even up to 6 kilometers per second in this 001 case, we still observe simple elastic compression of the diamond bulk. It is even more compressed than our previous simulations, but there's still no plastic deformation occurring here. Simply pure elastic deformation that is beyond the ability of the diamond algorithm to recognize. When we go above 8 kilometers per second and up to 10 kilometers per second for our simulations, which is reaching up to the terapascal range of pressures, we finally see 001 diamond break down. While the front is still elastically compressed, as can be seen here, a disordered region trails behind in a second wave. A closer look at the transition from the ordered to the disordered zone sees the formation of separate clusters of diamonds surrounded by a disordered mass. These recrystallized areas appear to have a high concentration of twinning as well. When we do a potential energy analysis of these zones, it shows that the recrystallized zones have a significantly lower energy compared to that of the disordered regions. These recrystallized zones help to attenuate the deviatoric stress on the material, leading to lower energy zones. Further analysis is needed for the exact cause of what is happening here, whether the diamond has reached a melting point or if solid state amorphization is occurring, as well as other possible measurements for the density and the growth of these clusters. In summary, we use the angular distribution function in shocked silicon to help identify transformed silicon phases, And in shocked diamond, we found a strong orientation dependence in the threshold for dislocation formation, as well as performing resolved shear stress analysis to help explain why some dislocations were not present. Additionally, high pressure simulations found disordered and recrystallized diamond when going above 8 kilometers per second for the Tursoff potential. Regarding future work, there is a lot of exciting news in the field of machine learning potentials for both silicon and diamond. In particular, the Olenek group at the University of Florida has an interesting machine learning snap potential for high pressure diamond simulations, although it still hasn't been fitted for defects in diamond. However, it could help to simulate the high pressure phases of diamond instead. Simulations of non-planar surface shocks in diamond are also of interest. During our ride-along shots for diamond at the Omega, we found that at 400 joule laser energy, our diamond samples seem to have completely amorphized. We don't exactly have a explanation for what exactly went on there, whether there was an error or whether our TEM analysis caused the amorphization to occur, but we think that it could be that non-planar surface shocks in diamond could have caused the entire sample to amorphize. So we need to do more simulations in there as well. We also want to try varying the void size in the diamond and observe its effects on the threshold for dislocation generation. I would like to acknowledge the Myers Research Group, in particular my partner Boy Ali, who handles the experimental side of things, and Professor Mark Myers for being my PI. I'd like to thank Dr. Rob Rudd, who is my mentor at Lawrence Livermore, who I couldn't have done this research without. And I would like to thank the Center for Matter Under Extreme Conditions for funding this research. Thank you. Are there any questions?
Great. Thank you so much for an excellent talk. This talk is open for questions. Either you can speak up or write your question in the chat.
Hi, Alex. This is Mathieu in Farad's group. And I have a question about the Omega experiments at 400 joule.
Mm-hmm.
So what was the velocity, the shock velocity you got in that experiment?
It's been a while since we looked at the numbers. I think it reached up to, I don't know what the shock velocity was, but I think our peak pressure was around 140 gigapascals, which is way below what we would expect to see for amorphization.
Yeah, right. Yeah, okay. Okay.
Yeah.
Thank you.
Sasha has a question.
Yeah, please go ahead, Sasha.
Hi, I have a question regarding voids.
Mm-hmm.
There was a picture like, I don't remember which is it, silicon or carbon. Nevertheless, there was like a void which was like filling by some species from the bulk of the crystal. Can it be interpreted as a mass transfer near the void? Yeah, this one.
Mm-hmm. I suppose so. There are definitely atoms that are jetting into the void here and are no longer being subject to the pressures of the shock or the rest of the atoms in the simulation. But that's not my area of expertise.
Okay, thank you.
Sylvia, please go ahead.
Hi, Silvia Pandolfi. Very nice talk. I had a couple of questions out of curiosity. The phase that you identify for silicon, for the high pressure phase, has this been seen experimentally or not?
Yes, it has been seen experimentally in nano indentation experiments in particular have observed the BCT5 phase of silicon. It is a known metastable phase of silicon. And although the beta tin is more expected for equilibrium conditions, it has been observed in more dynamic or high pressure conditions.
Yeah, and then that was my other question, because I've seen like those banding structures also in like some other MD. I think it's a Monyi et al. A PRB on shock compressed silicon, but it's more like laser shock compression. So I don't know if maybe the shock is different.
Mogmi et al. Yes.
Exactly. And then there is also one by Higginbottom, and they do see, well, actually also the Shitang Zhao sees the amorphous bands to have like a preferential direction. And I was curious to know if you have studied the direction of these bands and if that corresponds to the other studies? Like, what's the crystallographic orientation of these
Yeah,
bands?
so a lot of this research was based on Shiteng Zhao's work, which was studying those amorphous bands in silicon, although they were actually BCT5 bands with small amorphous pockets. And in his work, he described the direction of these bands as trying to adhere to the cone of maximum shear, which is along the loading direction and about 45 degrees away. However, the closest slip system to that direction of maximum shear was about 54.5 degrees, and that slip system is where these bands are forming along.
Okay, so you do see them in the simulation of at 55.
Yes.
54, sorry. Okay. Oh, okay, that's cool.
Yeah.
Thank you.
Are there any other questions?
You muted, Mark.
Yeah, okay. I just have a comment about the experiments of Omega. They were done at 3 energy levels. Okay, and Alex only quoted 1, but there were 3 energy levels. So the lowest one only showed elastic, and then the highest one is showing this weird amorphization which we have to resolve still, okay?
Yeah.
And,
Okay.
and Mark, you probably use quite a large faceplate. So what do you think would make the non-planar effects here?
It could have been just defects in the machining of the diamond sample itself, or just other defects in the faceplate. We're not sure.
Okay.
Yeah, we need to look more into it.
At the nanometer level, nothing is perfect. You see, although we polish the diamond, but if you go to the nanometer scale, you probably have irregularities of 100, 200, 500 nanometers, like peaks and valleys, and they can provide very strong concentration of stresses that could potentially trigger dislocations or even amorphization. That's our hypothesis, okay? And Alex is going to test it here.
Thank you, Mark.
Before we go to Felipe's question, there is one on the chat. Did you confirm that dislocations from DXA are 001?
Yes, we did confirm that they are from the DXA, they are along the 001 slip for the rectangular bands.
Great, thanks. Please go ahead, Felipe.
Thank you, Farhad. Hey, Alex, Felipe from Berkeley. Regarding the phase diagram in pressure temperature space for silicon, there are several reported phases like DHCP or simple hexagonal FCC. Did you see like any of these phases, or how is that your predicted shock Hugoniot points cross this phase diagram? Do they cross at the predicted phase, predicted pressures? For example, the beta T should appear like at around 10 GPa or so.
Yes, for the phase diagram, the predicted phases for equilibrium silicon are around 10 GPa for the beta 10 and around 11 GPa for the BCT5. But it is different for each potential. And for this modified Tursov potential, the BCT5 was the lowest energy phase for these conditions. But there were several other phases that were quite close. The beta 10 was quite close, and the IMMA phase was also quite close.
Okay, nice, thank you. And just a quick question. You showed us when you separated the different zones by potential energy, but how about kinetic energy? So is regions thermalized? Is the temperature like isotropic? Is it like still out of equilibrium, or these are out of equilibrium conditions?
So when I was looking at the kinetic energy of these particles, because everything is moving so quickly, there wasn't much difference there. And comparing the clusters to the rest of the disordered mass, there was almost no difference to be seen.
Thank you very much.
Hey, any other questions or comments? If not, let's thank Alex again.